I'm excited to really kick off with the roadmap to a cure. Firstly, I want to start by thanking all of our amazing sponsors for making yesterday, today, and tomorrow possible for all of our families to be here. A tremendous amount of the support to get families here through scholarships has been because of our sponsors, particularly Maddie's Mission. So I want to thank Maddie's Mission for really bringing families here and supporting that effort. People have come up to me just so grateful for the opportunity to sit in this room. And of course, it's our obligation for you to be in this room, but really we couldn't do it without the support of our sponsors. You'll see sponsorship titles around the room and around the event, but please thank the sponsors. We couldn't get this done without them. This is incredibly expensive, but it's a weekend that all of the families deserve, so thank you. In addition, I want to thank our team, the FAST team, particularly Laura. Laura Falgiano has unbelievable ability to run a meeting, and just so you know, like, the heavy lift of this has really been on Laura. And so, Laura, I don't know where you are because I can't see anything, but I would like to acknowledge you if you're here, so please stand if you are. And she's probably back there. And if she's not, let's just clap for Laura, because Laura has been amazing. Thank you, Laura. We love you deeply. And lastly, I would like everyone in the room to raise their hand if they are a family member. All right, so everyone look around. These are our family members. Raise your hand if you're a research scientist. Raise your hand if you're an industry member. Awesome. So what you can see is that we have every stakeholder in the room, mostly families, but also researchers and industry that's here to learn from us and learn from you. And it's really important that we share our story. And so engage and talk and learn and really learn about what these people are doing here. And to industry and researchers, learn about why parents are here and they care deeply for advancing therapies for Angelman syndrome. So, as most of you know, my name is Allyson Berent, and I serve as the Chief Science Officer for FAST. I have a couple of roles that I play. I'm also the co-director with my compatriot Jennifer Panagoulias, who you'll meet shortly, who, for the Angelman Syndrome Biomarker and Outcome Measure Consortium. And we're going to go over later today the learnings from that closed-door meeting that we had yesterday, which I hope was incredibly successful. I also stood on the stage a lot of the time, so I couldn't tell if people enjoyed it, but I certainly enjoyed it. So I hope everybody else did as well. So we'll share the learnings from that meeting yesterday. I also am the co-director of the International Angelman Syndrome Research Council, which is a pre-competitive collaborative consortium where we are leading a group of basically experts around the world that are not only working in Angelman syndrome but other neurodevelopmental disorders in order to learn and to fill our gaps and understand our gap analysis. And I am the Chief Development Officer of the accelerator that FAST started called AS²Bio, which we'll talk a little bit about today. And most importantly, I am the mother to 3 beautiful little girls, and this is Quincy. She is 11 years old, and she lives with Angelman syndrome. Here are my disclosures. So we heard a lot about the basics, but now I'm going to talk about the basics of Angelman syndrome. And hopefully everything you learned in the last session will prepare you and give you the tools to understand everything that I'm going to say as well. So Angelman syndrome involves a single gene on a single chromosome. And as you learned, there are 46 chromosomes in most of our cells. 23 pairs, one that comes from mom or maternal, and then one that comes from dad or paternal. And it's caused by a severe reduction in a single gene that is called UBE3A. And that gene sits on the 15th chromosome. It affects approximately 1 in 12 to 15,000 people, which could be 500,000 people in the world. And it's usually random. None of us, or very few of us, are carriers for this. There are some, but very few are carriers for this. It happens randomly in the egg, usually before fertilization. So this happened likely in mom's egg when she was being developed in her mother's body, which means that this is before we were even born, that this egg developed this mutation, a deletion or a changing of the letters of the gene. Each chromosome, as you learned, is made up of tons of genes, over 20,000 genes per chromosome, and it codes for different proteins in the body. So every gene that causes disease usually is associated with some protein that's not being made at all, or it's not being made well, and ultimately results in a change of function. So we learned that this morning, but hopefully we can relate this to Angelman syndrome. And so let's blow that up a little bit. Okay, here's the 15th chromosome. And our cells have one copy from mom and one copy from dad. And if we make that into a schematic, what you can see is that in neurons only, the copy from dad in me, in you, and in our children is silenced. It's silenced by something called a long non-coding RNA, complicated. You may see it as UBE3A antisense, or the stop. It stops the expression of the UBE3A gene in the neurons on the father's copy of the gene. But with Angelman syndrome, the mother's copy is not being read in all of the cells. In you and I, our mother's copy is being read in the neurons. The father's copy is silent in the neurons, and we have normal function. Well, you can make that decision. Somewhat normal function. But in our kids with Angelman, the mother's copy is generally not being read, or it's deleted. And therefore, they don't have expression of the UBE3 gene, resulting, as you learned from Emma, the UBE3 protein. Because the father's copy is silent, the mother's copy is gone, therefore they're null. The neurons have nothing. But in the rest of the body, the father's copy is not silent, so they're expressing the gene. And therefore, it's only a disorder of neurons. So this can happen in various different ways, which we're going to hear more about later. But some, and the most common way, is a deletion of a segment of the mother's copy of that gene. The next most common way is a mutation within the UBE3 gene, meaning a letter is misspelled, or a little piece is missing, or a little piece is added, making the gene not read well, which makes them not make a protein. In a small proportion, the silencing of the father's copy is also silenced on the mother's copy. And that's an imprinting center defect, or UPD, where instead of a mother's copy and a father's copy, there happens to be two father's copies. And that means they're both silent. Again, the result being a lack of expression of UBE3A in neurons. And then there's one group, a very small proportion of the population, that has something called mosaicism. And that is an incredibly rare group, but that group ultimately is a key to a lot of information that we'll talk about. And what that means is that it didn't happen at the egg stage, but the mutation, or whatever went wrong, happened after the egg and the sperm fertilized in the embryo. So it happened very early, but what happens is that most of the cells of the body are not expressing maternal UBE3A, but some of them are. And we'll talk about that. So the function, I don't need to tell you now, which is wonderful, because you've just learned that. right? UBE3A is an enzyme, the E3 ligase. It tags proteins for degradation or to keep them around for longer. And by doing that, it allows for neurons, all of those proteins being cleaned up in that space allows for neurons to communicate well. And if you have too many of one protein or not enough of another protein, the neurons are not going to communicate very well. And that results in the symptoms of Angelman syndrome. And that cleanup and that what we call homeostasis is required for normal neuron function in the brain. And our neurons are what allow our brain to think, allow our muscles to move, allow us to perform all of the functions that we do. So this is called, you may hear the word synaptopathy. It's called that because the communication between two neurons is what is abnormal. And so the synapse is that junction where one neuron is talking to another neuron. And those two neurons need to speak because the second neuron talks to our muscles. And if we can't get the message from the first neuron to our muscles, how are we going to walk? How are we going to talk? How are we going to rest, sleep? All of our functions are intrinsic and depend upon neuronal communication. And that is disturbed when you don't have normal function at that area, the synapse. And it results in the symptoms of Angelman. If we can't communicate one neuron to our muscle to say, when I take a step, I'm going to activate this leg and relax this leg, and now I'm going to activate this leg and relax that leg. That's communication. And if we can't do that quickly as the neurons are firing in milliseconds, microseconds, then how are we going to coordinate thousands of muscles in our face, our tongue, and our voice box to say a single word? That's all communication of nerves to muscles. So you can imagine how if you don't have that communication, you have this buildup of proteins in that space, things are going to seem very foggy, things are going to be very slow, and things are not going to be able to communicate at a pace in which normal function can happen. And that results in the symptoms of Angelman syndrome. One thing I'd like to highlight is that a majority of the population has a genotype of deletion. Deletion means an entire segment, not just the gene, has been deleted. Now, there is something called an intragenic deletion, meaning there's only a deletion within the gene, and we bucket that with mutation because it's only affecting the UBE3A gene. And I know a parent in the community had a question about that. The deletion generally involves a big segment of the chromosome. So if we blow that out, here's the UBE3A gene, here's the big segment that's been deleted. So this could be like 6 million base pairs of DNA. Imagine that, 6 million base pairs of DNA that have just been deleted, gone. Where a mutation might be 1 base pair of DNA that's the wrong letter. That's the difference between a deletion and a mutation. So it's important we understand that, because with deletion, we have all of these genes that are sitting around UBE3A that are missing, that may have some function, that contribute to why individuals with a deletion of Angelman syndrome may be a little bit more symptomatic than those with a mutation or UPD or ICD, where they're not missing these other genes. Well, let's talk about those other genes a little bit. There are the GABA genes that we hear about. All of these genes may contribute to seizures, to sleep, to motor function. And so we don't want to forget about those genes, because as we've moved toward addressing, replacing UBE3A, we really need to move toward thinking about addressing these other genes outside of UBE3A. And when we think about those genes, we want to dig into the literature and say, which of them actually have clinical function, right? Our kids are missing half of their copies of those extra genes. They're fully missing UBE3A in neurons, but those other genes are not silenced. So they're being expressed on the father's copy. They're just not being expressed on the mother's copy. So if that's the case, we call that haploinsufficiency, or half of the expression that they might need. So if we look at those genes and we look into the literature of the clinical signs associated with those extra genes, what we learn is not all of them likely are related to disease. The GABA genes, those two GABA genes, do seem to have some individuals that only have mutations or loss of function of one copy of those genes in which they have some clinical symptoms. Those symptoms might be associated with seizures, some intellectual disability, and maybe even some learning disabilities. Sleep may be impacted, so you can see the overlap of the Angelman syndrome symptoms and those genes. And so we don't want to forget about them. But the two genes that rise to the top is GABA B3 and GABA G3. So we need to think about, can we correct those as well? So with all of that in mind, UBE3 alone, without even thinking about those extra genes, results in all of the symptoms we live with. And just to educate those who don't live with Angelman syndrome, because I do not need to educate those of us that do, it is associated with a universal lack of speech, significant sleep disturbance, ataxia and incoordination, where some individuals don't even walk, impulsive and hyperactive behaviors. Sometimes that can lead to aggression and frustration, an inability to live an independent life, and all of the activities of daily living that are tremendously impacted. But what I don't want anyone to forget is the impact it has on us, parents. Inability to maintain employment, loss of sleep, anxiety, social isolation, fatigue, chronic fatigue. Imagine sleeping 3 to 4 hours a night, not just during the newborn years, but for 25, 35, 45, 55 years, because our kids are not degenerative, and they live a normal length of life, we believe, just not a normal quality of life. And who is impacted by their lack of sleep? Of course they are, but what about every caregiver that has to take care of them for the rest of their life? That is profoundly impactful to families. So I'm speaking to the drug developers in the room. When we think about the symptoms we're addressing, we cannot forget about the impact that these symptoms have on families. And that is what meaningful is. How can we address the symptoms of this disorder that are meaningful to families? It's not always only to the child or to the adult that's living with Angelman syndrome. So I mentioned mosaicism, and I'm going to go back to that, because anybody in this room that has a child with mosaicism, I just want to thank you, because you certainly, when we got our diagnosis, saved my life. When I learned the capacity of individuals that are expressing 1 to 5% of maternal UBE3A in their cells, meaning 99 to 95% is gone. They only have 1 to 5%. Those individuals may have some speech. They don't have seizures, and they walk beautifully. That's a different child to the 99% of us where our kids live with no maternal UBE3A. What does that tell me? 20%, they can speak in sentences, potentially, and 40% may not even be diagnosed because they are mistaken as neurotypical. Imagine that. Imagine that. And what that tells me as a doctor is that we don't need a lot to make a huge difference. Of course, I want 40% or more because I want a neurotypical child. We all do. or many of us do, but 1 to 5% is a quality of life improvement that I dream about. And I think most of us do. And we learned that because of the Mosaic children and adults. And so for that, I'm grateful, but it allowed us to think about drug development in a little bit of a different way. So how are we gonna get there? How are we gonna address it? So this is the roadmap. Okay, we used to have 4 pillars, and I'm gonna explain the 5 pillars, but your book has everything in there about the pillars and the why. So we can replace the missing UBE3A gene or protein, pillar 1. We can unsilence the paternal allele, pillar 2. By unsilencing it, we will allow it to be read in neurons, which is essentially similar to replacing it, but it's a different strategy on how we think about the molecular way to address that. Pillar 3 is thinking about the genes outside of UBE3A for the deletion, for UPD and ICD, because they all have different genes that are probably contributing to the phenotype in those genotypes that are different than mutation. Pillar 4, everything we learned about from Dr. Margolis about the downstream targets. How do the downstream targets affect the function of the synapse and the neurons, and can we hit those targets in a way that could benefit individuals with Angelman syndrome? And then finally, pillar 5 is all the things we need to do to set up and be prepared for clinical trials in Angelman syndrome. So this is just a gateway into everybody working on this. Pillar 1, AAV gene replacement therapy, lentivirus hematopoietic stem cell gene therapy. I know these words sound really big and scary, but we're gonna go through them one at a time. Enzyme replacement therapy. All of those are to replace the UBE3A gene that is missing. Pillar 1. Pillar 2, stop the stop. Unsilence the father's copy of that gene. We can do that with an antisense oligonucleotide, or ASO. It's all in your glossary. Don't be overwhelmed. Just listen and absorb. It's all in there. You're going to be hit by this time and time again over the next 2 days. I promise you, you're going to walk out of here and you're going to understand it. Artificial transcription factors, CRISPR gene editing, and miRNA or siRNA. All of those technologies can unsilence the father's copy of that gene. How are we going to deal with those genes outside of UBE3A? We're going to hear a talk later this afternoon about how we can CRISPR activate and turn up the notch of those haploinsufficient genes to increase their expression on the father's copy in which they are read, because it's not UBE3A, and we can increase that expression. Downstream targeting, we have small molecules like drugs from Neurin. We're going to hear a lecture from Helix about some drugs they're working on, from Roche, and from Brown University. And then critically preparing for clinical trials, which are all the ways in which we have the models that we've developed, the endpoints and the biomarkers that we're working so heavily on, and ensuring we have policy and regulatory strategy so that the regulators hear what we're doing and help to support it. So that's another way of looking at it, which is in your program, is those 5 pillars: maternal replacement, unsilencing dad, adjacent genes, downstream targets. Let's get prepared to accelerate toward human application. Let's start with pillar 1. That's a neuron, and we need to get UBE3A into that neuron because it's missing. And there are a couple of ways that we can do that. One being with AAV gene replacement therapy, where we take a virus, which is a healthy virus, where the bad parts have been taken out of it, and we deposit the UBE3A gene inside that virus. That virus is then injected into the fluid around the brain, whether that's through the fluid at the base of the skull or the fluid through the brain into the ventricle, or we're going to hear a talk tomorrow about the potential to actually inject it in the veins, and the virus can cross the blood-brain barrier, go from the veins to the brain. That would be amazing, and we'll talk about that, but that's really something that doesn't have yet that path in humans. We don't have that long track record yet for that very new and very exciting technology. We'll talk more about that as well. We can do it a different way. We can take cells, as Emma showed you, outside the body, our own blood cells. We can put the UBE3A gene into those blood cells in a dish. Then we can put them back into the body, if we make a little space for them in our bone marrow, for them to deposit and create a factory in our bone marrow, to then release the cells out of the bone marrow, the blood cells, they're called blood stem cells, and those blood stem cells cross the blood-brain barrier, go into the brain, distribute throughout the brain, touching almost every neuron, and release UBE3A to get into those neurons, to be read, for that protein to function. So that's called hematopoietic stem cell gene therapy. And then enzyme replacement therapy. What if we can take the UBE3 protein and just put it into the brain? So we're going to hear about that as well. So, gene replacement therapy. You don't need to read this slide because I'm just going to summarize it for you. But what I want you to see is that so much work and time and money has gone into this because of you. You have funded all of these experiments, and these are animal experiments. These are mouse experiments. And we also have now monkey experiments, showing that if you replace the UBE3A gene, you can correct the behaviors of the mouse that may be somewhat translational to people. And we can do that with AAV gene replacement therapy. So what you can see is that the graphs, you're going to see high, low, high, right? When you see correction to wild type or normal, which Dr. Samako explained to us, wild type is the normal mouse or the neurotypical mouse. If we can get back toward neurotypical and away from Angelman syndrome, we are improving the behaviors of these mice with these technologies. And so this gene therapy, on the top is the AAV, at the bottom is the HSC, but you don't really care about that. I think you care a little bit more about this, where let's just look at the reality of it, right? So this is a program, the hematopoietic stem cell gene replacement therapy, where you can see a mouse on the left with Angelman syndrome. And that mouse is having a hard time. He can't keep up. He's hit his back legs, he's maintained in this system, but he's really falling behind. In a single mouse, after gene replacement therapy using hematopoietic stem cells, look at that same mouse. It doesn't take a scientist to look at that and say, well, hell, can you do that to my daughter? I'd like her to walk like that. So you can see the benefit of these animal models to show us the possibility of improving gait, for example. One thing about this program, which we've been funding since 2016, is that it used something called an MNDU3 promoter. Well, you don't care about that, and Dr. Kohn is going to talk to us about that tomorrow. He's our keynote in the morning, and I really encourage you to come and listen to this talk, because it's really important for you to understand this. But we had to change this promoter because this promoter was associated with some safety challenges in the clinic, in humans with other programs, not in Angelman syndrome. So before we went to Angelman syndrome, we said, we're not going to use the promiscuous promoter that might have risk. We're going to find promoters that have 15 or 20 years of experience where we can feel the safety track record is stronger. So let's see, what can we do with the new promoters? Well, I want you to look at the top left, which is a wild type or neurotypical mouse. I'm going to have you look at the top right, which is an Angelman mouse. And the bottom left and the bottom right are two new promoters that have a better safety track record than the prior promoter that was done in that early work. So look here, top left, top right, bottom left, bottom right. You can see the wild-type mouse is getting to the end with no trouble. Promoter 1 and promoter 2 are having a race. And Angelman untreated is having a really hard time. Doesn't take a scientist to look at that and say, that's different. We've corrected the balance and motor function of that mouse, that single mouse. When you see profound effect like that, it gets you really excited that there's the possibility of this type of therapy improving the symptoms of Angelman syndrome. What gets me more excited than that, as someone who understands the research, is to say, okay, Angelman's at the top. Look at UBE3A, which is the third column, where there's no green. Neurotypical, you see green, the wild-type mouse. Promoter 1 and promoter 2, I think I see green. Well, the green is UBE3A. Well, hold on, let's dive in a little bit more. I see a lot of UBE3A, and it looks like the red are the neurons, and the UBE3A is in the neurons. All right, let's dig in a little bit more. Wow, there's a lot of UBE3A in those neurons. And that's why you can see the behavior of those mice gets so much better, because this is a mouse. And remember, a mouse is not a human, and we don't know how this will translate to humans. But what we do know is that I call this the field of poppies, because that's what it looks like. And that's very exciting to see, because with most therapies, we don't see that. And so that's an exciting program, all because of you and your funding to help support it. Let's move to pillar 2. Pillar 2 is unsilencing the father's copy of the gene. You could do that, like I said, with antisense, oligos, zinc, fingers, miRNA, shRNA, siRNA, CRISPR, so many things. I can roll these terms off my tongue because you guys now know what they are, thanks to the education that you got this morning. Let's unsilence that father's copy. Well, how do we do that, and how does that look in the animal models? ASOs can rescue phenotype in the animal model. In an adult, there was some of the phenotype that was corrected. So we have optimism that in older animals, maybe we can see benefit. And that was enough for us to be able to push that through to human application, which we'll talk about, which is incredibly exciting. Zinc fingers, we were able to see that we can unsilence the father's copy, and you could see the brown at the top, no brown in the middle, and the brown at the bottom. What does that mean? UBE3A has been restored into the neurons of the brain. That's exciting. That's a positive result. And then it also corrected the behaviors in the mouse model of Angelman syndrome. So super exciting. What about CRISPR gene editing? Same thing. These slides don't mean anything to you in terms of you see a high black bar, you see a very low white bar, and you see an in-between gray bar. The in-between gray bar is what was corrected in one experiment using AAV CRISPR delivery in order to deliver the editor to the brain and deliver unsilence and deliver UBE3A to those neurons. And then on the right, you can see that there's lots of bars of correcting the phenotype of UBE3A, of Angelman syndrome in the mice. But this probably means a little more to you, and this is my favorite video. Sorry, Shauna, I know this is your video, and I steal it every time. But it's so important for families to see. We have the wild-type mouse on the left, the untreated Angelman mouse in the middle, oops, and the Angelman-treated mouse on the right. What's more important to me in this video, similar to the other video for HSC gene therapy, is that these are adult mice, not newborn mice, not neonatal mice, not mice that are in utero. These are adult mice, adolescent mice, teenage mice that are having benefit after birth, well after birth, in order to rescue these phenotypes. We don't know how that will behave in humans. We have no idea. But we don't know it won't improve phenotype in humans. And the only way we're going to know is if we try. And there's reason to believe, based on what you're going to hear tomorrow, with the ASOs in clinical trials in both adults, young children, and adolescents, that benefit is being seen across the board for all individuals living with Angelman syndrome. And so that's really optimistic that maybe that therapeutic window that a lot of people like to talk about is different for neurodevelopmental disorders than it is for neurodegenerative disorders. Let's talk about Pillar 3. Pillar 3, we have a program where we are upregulating the haploinsufficient genes in the deletion genotype. We already talked about that. This is a group out of UCSF. Dr. Nadav Atia is going to talk to us later today about the program that we're working with, a collaboration between Yale University, North Carolina State, and University of California, San Francisco. And this is where we're upregulating those genes to try to see if we can have a benefit in improving the expression of some of those genes. And I'm not going to give it away, I'm going to let him share his data, but what you can see here is that we have found constructs for humans that can increase expression of those genes that we think really matter, which is very exciting. And then finally, Pillar 4, those downstream targets. Each one of these downstream targets has a different path that they are addressing. And we learned that there are thousands of paths that we might be able to address. And each one of these programs, Neurin, Brown University, BDNF Analog, OPC Rescue, Allogabat from Roche that they're going to talk about tomorrow, and Helix you're going to hear about later today, all talking about different constructs that might affect the synapse and improve function. And then finally, where does that put us? It puts us to say, this is overwhelming, there's a whole lot to be excited about, but how do we compare this to that or that to this? I don't understand. And so somebody did a study where they looked at if we replace UBE3A at different time points, prenatally, at birth, in a young animal, in an adolescent animal, or in an adult animal, you could see as they get older, you get less rescue of the behaviors, which led people to believe the younger the better. And that's logical. But what's interesting is that if you look at the actual therapeutic modalities that are translational to humans, and you use the mouse model that's truly translational to a human, a mutation model of a mouse where their UBE3 gene is not functional, it's not expressing on the maternal allele, just like a mutation in humans where the other model is not that model, and you actually give them AAV gene therapy, HSC gene therapy, ASOs, CRISPR gene editors, or ATFs, well, wow, that heat map looks a little different. A lot less red, a lot more green, whether you're an adult, you're an adolescent, or you're a newborn, there's phenotypic rescue at every age. And we have reason to believe for functions like cognition, learning and memory, motor, behaviors, EEG, sleep, biomarkers. If we look at all of the behaviors that we translate to humans, there's reason to believe we might be able to have a benefit in the lives of all humans at all ages. The only way we're going to know the answer to that is when we test these therapies in humans at all ages. And that's very exciting. And so I just want to direct you on your table. There's a journal that FAST started, thanks to Ed Weber, called the FAST DART Journal. So basically, this journal, which you guys can look at, is going to be online, available to all, in order to be able to publish analyses, papers, and review articles for Angelman syndrome that could benefit our learnings. And it's meant for the scientific community, but everyone will have access to it because it's free. And one paper that's in there that I want you to take a look at that I'm really, really proud of is this meta-analysis where we took all of the studies that have been done, over 40 studies, put them together and said, how do rodent models define the potential for human benefit? A translational review for Angelman syndrome. Rather than people and scientists picking one paper at a time and trying to put it together to make a story, we put it all together very scientifically to say this is the story. Look at that heat map. The reinstatement model contradicts the gene delivery model, which is more translational to our kids. And so we really need the data in humans because there's too much contradiction in animals to truly understand what any of that means. But there's possibilities, there's potential to expect we might see profound change. We also have a list of all of the different phenotypes in these animal models for the research community, so you can understand what model is testing what and how that translates to humans. And all of the models that are out there, as Rodney Smacko said earlier, we have way too many models. But 95% of people use one model, and that is Dr. Zhang's model, the mouse model. That is an imitation of a mutation, non-functional loss of function mutation from 1998. And that's what most people use. So we welcome you to take a look at that. So now let's move to the fifth pillar, accelerating and preparing for clinical trials. Because those faces are what matter, and that's why we're here. So the efforts to support clinical trial readiness have been vast and incredibly expensive and taken more time than anybody ever thought. But we're getting there and we're doing it. One of those is creating the tools, the animal models. We have rats and pigs and mice galore. No more models, please. We're good. Cell lines. We have every cell line of every genotype that is available pre-competitively for anybody to use at eBISC, that any company could have access to, that's non-proprietary, so nobody's waiting for academic collaborations and research grants and contracts. We made it available for anybody to use at any time, and that was through a collaboration with Yale University, and Youngwei is going to talk about that this afternoon. And we have different ways, organoids that you saw earlier, these little mini brains, all of those things you heard, these are those in vitro tools. And this is all on our website as well for the research community that wants to have access to this. And then InSync, International Angelman Syndrome Research Council, which I talked to you about earlier, is a collaboration we have with the Simons Foundation with the goal to fill gaps in Angelman syndrome drug development and other neurodevelopmental disorders. So Angelman syndrome happens to be relatively far advanced in terms of drug development activities compared to many of these other newly diagnosed genetic neurologic disorders. And it's unfair for us to take everything we've learned and live in a silo. So we invite other neurodevelopmental disorders to the table to not only help advance them on where they are, but they have learnings that can help advance us on where we are. Everyone goes at this from a different angle. And if there's anything that we can learn from them and they can learn from us, we advance the field together. And that's the only way for us all to make a difference in the lives of these individuals, is to get out of our silos, work together, and advance the field. And this has allowed that to happen in a really great way. Advocacy Day on the Hill, that's part of our Pillar 5. Ryan's going to have a talk, Lunch and Learn today about this. His efforts here, and him and Jennifer and Amanda Moore, she's hopefully in the room somewhere, have been incredible. Getting you all out there and fighting for what's right, fighting for what we need in order to be able to improve the lives of our children. That's been incredible. The externally led patient-focused drug development meeting that most of you participated in has been an unbelievable wealth of information that we've been able to leverage, and our entire day yesterday was around this concept, and Jennifer's going to talk to you about that in the updated ABOM talk shortly. So I don't want to give this away, but ultimately what we know is what impacts our daily lives the most, and what are the priorities in impact for treatments. And what was so clear for me out of all of this was that what a neurotypical family might consider a minimal change, an Angelman family feels is profound. If we can improve one domain, communication, independent living skills, motor function, sleep, cognition, we would take it, because any of those things will improve our children's lives and ours. And 342 of you made that very clear. We cannot do that without you, and we are so grateful for your participation in these activities. And then we have a natural history study. Again, all of the work you families have put into this. And I can't thank enough the natural history study teams at Boston Children's and Rady's and Colorado and all over Canada and the United States. These teams, over 19 and a half years, has put together data on over 650 of our kids. Over 19 and a half years to understand the trajectory of developmental change so that we can compare that to natural history data. And why is that important? Well, this is why. The top is the data presented last year by IONIS for the ASO clinical trial. And that study showed, because it's open label, the only thing they can compare the treatment group to is the natural history of the disease. How did individuals not treated do compared to our individuals that were treated? On the bottom is the ultragenics data. And I'm not here to compare one to the other. All I'm here to show you is that on the top, black is the change in natural history over time. Red is the change in treated Angelman patients after an ASO over time. In cognition, communication, the things we care most about. And you can see the trajectory both with the data at the top, IONIS, the data at the bottom, ultragenics, just presented in two different ways, that both of them have completely changed the trajectory compared to natural history. If we didn't have you all participating in those natural history studies for so long, there's no way we would have that data for them to say, I believe there's a potential treatment effect here. We are going to move into a phase 3 clinical trial, which has to be a controlled study to truly prove if these drugs are working. Without that natural history data, that's just not possible. And this has been all thanks to our community, to the natural history team, to all of our sponsors, and the support and collaboration of the ABOM, which is the Angelman Syndrome Biomarker and Outcome Measure Consortium. That was started as a collaboration between FAST and the ASF in 2016 as a pre-competitive space that Jennifer's going to talk about. And where we are today in 2025 is that we've went from a $50,000 budget to having spent over $5.1 million on this since 2016. We have everybody around the table, including the FDA, who is supporting the efforts for understanding what is a minimal, meaningful change. And Jennifer's going to talk more about that shortly. What are the domains that matter? How are we going to measure them? And how are we going to put them into clinical trials? This is so vitally important for us all to understand why clinical trials are complicated, because we have to measure all of these things, and we're going to talk a lot more about that tomorrow, but you have to understand why we have all of these assessments for our kids, because we have to understand what can capture change. This isn't for you to read, it's for you to understand. It's a lot of work, it's a lot of money, and this is where your dollars go, to support these efforts, for us to be able to get over the finish line, for all of these amazing sponsors that are sitting in this room to do everything they can to help our kids. And that's why we're here. And so that is just a testament to the commitment. So hopefully what you can see is that every platform that we're talking about may benefit different targets. Each modality may lead to different amounts of drug or UBE3A in the brain in different places, and that may all have a different clinical effect on our kids. Different families are going to have different preferences. Some people may be very uncomfortable with a single treatment gene therapy. Some may be very uncomfortable going under anesthesia every 3 months to get a lumbar puncture to have an ASO delivered. Some may only want an oral pill for their kids, and some may never want to enter a hospital and will only do a remote clinical trial because it is too much energy, effort, and challenge to get their children to be seen in a hospital in a clinical trial setting. So these are all things we have to think about as an organization to meet the needs of every one of you, and we work really hard to try to do that. And what we also don't know is, what if combination therapy is the best therapy of all? What if we need an ASO with a gene therapy? What if we need a small molecule with an ASO or with a gene therapy? How are we going to know if we don't develop all of them and support those developing all of them? And that is our role. Because we do know the more options we have for our kids, the better chance of them having something that leads to a meaningful change in their lives and ours. So the standard drug development process looks like this. For every 15,000 drugs that are in early discovery, that are in a dish, that are in a mouse, that are in an organoid, one gets approved. What does that mean? We have to address all shots on goal. But what does that cost? 3 to 10 years in preclinical, 2 to 3 years in all of the safety studies required by the FDA, 3 to 5 years for an early phase study, 2 to 5 years for late phase studies? Well, let's just do the math. That's a lot of money for one program. So what happens is that we wait for pharmaceutical companies who, in our mind as parents, have all the money in the world. Yes, you industry, we think you have all the money in the world to support the development of these programs. But guess what? They don't. So they have to make priorities. They have to think about what has the highest chance of success, because we have to fund what we believe can be successful to maintain our pipeline. They can't take every shot on goal, even though they might want to. So that leaves this area, which we call the Valley of Death, where we have a promising candidate in a mouse and a dish, and we have to understand how it behaves in a human. That Valley of Death costs somewhere between $15 to $25 million per program. Who's going to pay for that? Industry might not. Yeah, so far it's been you guys paying for that. So thank you for filling this Valley of Death, because it's the only way we can get drugs to patients. And what I want to share with you is that 10 years ago, and I know a lot of you that have been here for year after year wait for these slides because you want to see the progress that's being made, and it brings me more joy than you know to share these slides. 10 years ago, we had 5 programs in early development and not a single program in a clinical trial. 8 years ago, after we had our first large infusion of funds, thanks to the generosity of a single family, we had 15 programs, 2 in clinical trials, and multiple headed toward clinical trials. 4 years ago, 34 programs, 3 in clinical trials, multiple headed toward clinical trials. And in 2022, the stock market crashed. Those 34 programs went down to 24 programs. And that is the chutes and ladders of drug development, and it happens. And we had an awakening of the fact that we can't wait for everyone to do this for us, because they might not. And when we lost 10 programs, it was devastating. But a year ago, we did not stop. We kept on going, and we went from 24 to 27 last year. And where we are today is we have 30 programs. A lot of these are undisclosed, so they're not going to be on our website. Just I know Megan Edberg is having a heart attack. They're not on our website, but I want you to understand how many people are working on Angelman syndrome. Of those 30 programs, we have, count them, 1, 2, 3, 4, 5, 6 in clinical trials. Our first gene therapy in a clinical trial. We have 3 in IND-enabling studies, which means they're going to be in clinical trials, hopefully. If those studies come out positive, because they can still fail, they will go into clinical trials in the near term. And 16 of those are being pushed by your dollars. That's important for everyone to recognize, is that your dollars are going so far, but it is not easy to get there. The pillar 5 is moving rapidly as well, equally well. And as we move forward, we have a lot that we should be proud of. Numerous potential therapeutic platforms have been invested in AS. Angelman syndrome is unique with many, many elegant gene-targeted therapies and opportunities underway, promising clinical trial results we have seen to date, which you're going to hear all about tomorrow. And FAST has focused on identifying the scientific gaps to accelerate all potential strategies and support all shots on goal, because we have no idea what the human experiment is going to show. And we have to make sure that we find something for anybody who wants a therapy. Traditional drug development, unfortunately, has failed rare disease across the globe, not just Angelman syndrome, and that's because money is drying up, investment is low, and companies have changing leadership, and they change their priorities. And sometimes those priority changes happen overnight. But we're not gonna let it fail this one, because FAST will continue to dream big, because you guys asked us to. This is about parents and their dreams. So this is why FAST decided to start the drug accelerator, AS²Bio. And AS²Bio is really meant to take venture philanthropy from patient advocacy and advance that into a disruptive accelerator. And that is the ecosystem of discovery in mice to discovery in human. And the only way we could do that is with this team. And there's so much that has gone into that, through the support of the NIH and Yale University for the CRISPR program, which you'll hear about tomorrow, through the support of UCLA and Don Cohn, who's here and being our keynote tomorrow, and CIRM, the California Institute of Regenerative Medicine, who believes in this program and is advancing us to an IND, through AS²Bio, and I'd like to just acknowledge, not only did our IND clear in April that everyone was really excited about, but yesterday it was announced that the first patient was dosed. And I would like to acknowledge a team that is sitting in this area that made that happen. The Mavericks team is here, most of them, some of them are online, and none of that would be possible without this incredible team who believed we can help make a difference for Angelman syndrome. And we don't know what's going to happen, and we don't know where the data is going to go, but they never stopped believing, and they worked their butt off to get us here. So I could not be more proud of that team at that table, so thank you. Ultragenics has advanced the ASO program that we started, and this was before that AS2 was initiated, and thanks to them, we were able to do that. We are so proud of that collaboration and our collaboration with everybody, Ionis and Oak Hill. We are so proud of Encoded. All of our programs, we don't help stopping to support everybody. But it started with Ultragenics and a dream. And that led to Mavericks, Courageous, Transformatics, and other programs that we're actively working on. So something that's always important to remember is that it always seems impossible until it's done. Thank you.